Okay, so the next trend we're going to talk about, even though we said the last one was the last trend, this is still a trend, but this has to do with you being able to understand electron configuration. So it's not as simple as looking at periodic position. This trend is magnetic properties. And when you think of electrons, remember we talked about the electrons behaving as tiny magnets, which we talked about when we did the whole spin thing with the orbital diagrams in the last chapter. And when you have two electrons in the same orbital, they actually are opposite in spin. If you recall, we had the spin up and the spin down arrows, and they actually cancel each other out. And what this helps us determine is why things are magnetic and things aren't magnetic. So if you have unpaired electrons, the actual atom exhibits magnetic properties. So if you look at the electron configurations, it would be having only a singly occupied orbital.
So a substance is called paramagnetic when it has unpaired electrons and it's weakly attracted by a magnetic field. So this would be any time a given sublevel is not filled, there has to be at least one unpaired electron, and consequently the elements are paramagnetic. The degree of paramagnetism, though, it's if you only have one unpaired electron, you're going to be very weakly attracted, whereas if you're something like manganese, where you have 5 unpaired electrons in the 3D sublevel, that's going to be strongly attracted. In fact, that's got a special word called ferromagnetism, ferromagnetic, but we're just going to stick with the paramagnetic, and we're not going to go into details about ferromagnetic. A diamagnetic substance is not attracted by a magnetic field, and this is because it has only paired electrons. So this would be when a given orbital is filled, or the last orbital is filled. So, for example, the alkaline earth metals have paired electrons in the s sublevel, which is the outermost sublevel, which means they are diamagnetic. The noble gases are diamagnetic because all of their electrons are paired. And like the transition metals, zinc and cadmium and mercury would be diamagnetic. And those are the only ones, yeah. So those are the ones that are diamagnetic. If they have any unpaired electrons at all, they're called paramagnetic.
Okay, so let's look at some examples. So we are going to be doing diamagnetic, basically meaning it has paired electrons, so it's unattracted to a magnetic field, or paramagnetic, having unpaired electrons, so it is attracted to a magnetic field. So iron. Iron is, gosh, I can't see that far.
Argon 18. Just do the noble gas thing.
Oh, you want me to write out the electron configuration?
Yeah.
Okay, so let's do argon, and it would be 4s2, 3d6. Okay, now if you think about the orbital diagram, you have 6 electrons in the d. You would have 1 paired orbital and 4 unpaired. Okay, so since you have unpaired electrons, that makes this paramagnetic. Which means that it is attracted to a magnetic field.
Okay, if you do calcium, calcium has the electron configuration argon, 4s2. It has 2 electrons in the s sublevel, which is all that sublevel can hold, which means they're paired, so it's diamagnetic.
Okay, and the last example is antimony, which is krypton, 5s2, 4d10, 5p3. This has 3 unpaired electrons in the p subshell, so it is going to be paramagnetic.
What we're going to do next is summarize all these trends that we've talked about, because it is a lot of information, and what you need to understand. You need to be able to explain on the AP exam, but you also need to know the trends and what causes them. So we're going to go through all those again.
Okay, so the first trend we talked about was atomic radius. And remember, the atomic radius is the distance from the nucleus to the outermost electron. And this is determined by the number of energy levels and what we call effective nuclear charge. So when you do your explanations, you're going to want to use those terms in your explanations. And in general, the trend increases from top to bottom in a group and decreases from left to right in a period.
Ionic radius. The negative ions are larger than the neutral atom. Positive ions are smaller than the neutral atom. Trends within cations and anions are the same as the atoms. So sodium is bigger than magnesium, which means sodium positive will be bigger than magnesium positive. Actually positive too. And isoelectronic ions are the smallest when the nuclear charge is largest.
The next trend we talked about was ionization energies. The ionization energy, when you use your explanations for this, you're going to be determining this by the size of the atom and to a small extent the subshells. This decreases from top to bottom in a group and increases from left to right in a period.
Electron affinity is also determined by size as well as sublevel. It refers to the amount of energy that's released when an atom accepts an electron. It decreases top to bottom in a group. It increases left to right.
Okay, the next was electronegativity. Remember, this is the one that's determined only by size. That was the Pauling scale. Your trend for this is it decreases from top to bottom in a group and increases from left to right in a period.
And the last one we're going to talk about, okay, so we did not discuss metallic character, but this is also a periodic trend. And we're going to go in the next two videos are going to go over metallic and non-metallic character. But metallic character is related to how easily an element forms a positive ion, which means it's determined by the ionization energy. The lower the ionization energy, the easier an element forms a positive ion, the more metallic it is. So metallic character has the same trend as ionization and it's tied to ionization energy. So it increases top to bottom because ionization energy decreases. It decreases left to right because ionization energy increases.